This video is going to be on the mean value theorem. And also Rolle's theorem, which is very similar to the mean value theorem. So first, we're going to look at that, which is MVT for short. And we're going to look again at the formal math definition, and then we're going to kind of see how it works. So we're going to say the formal definition is let f be a function that is, and there are two criteria that need to happen. First, it needs to be continuous on the closed interval from a to b, so there has to be some limitation to the domain there. And it needs to be differentiable on AB. And notice that when I went from continuous to differentiable, with differentiable I used parentheses, because if we have endpoints and the graph stops there, we aren't differentiable at endpoints. So we want to make sure that we have those open parentheses like that. So if this is the case, if it's continuous and differentiable, then there exists a point C on AB. So C is somewhere either in between A and B, or it could equal, no, it couldn't be. It couldn't equal A and B. It has to be in between them. That's because there's no brackets here. So C is something in between A and B. There's some C in between A and B such that the derivative of C so this means the slope of the tangent line at that point, so the instantaneous rate of change of C, is the same as the average rate of change from one endpoint to the other. So at some point on there, that's going to happen. So here is our first example. We're going to say given that f of x is x to the third minus x, and you're looking at the interval from 0 to 2, use the mean value theorem to show that f prime of c is 3. So we're saying the instantaneous rate of change at the point C is 3. And then after we do that, we want to find C. So first, before we can even use the mean value theorem, we have to know that it applies to the problem. So we need to know that our problem, our function is continuous on AB and that it's differentiable on AB. So if you guys remember, the things that would keep you from being differentiable would be any discontinuity, so that would be a vertical asymptote or a hole of some sort, anything that would make the graph not continuous. Other things that would keep the graph from being differentiable would be a sharp corner or a cusp, vertical tangent line, or if you guys recall when we were looking at the limits, when we were finding limits and we were using them to find derivatives, we knew that the left-hand limit and the right-hand limit had to agree with each other, and that's what means that we can't find the derivative of an endpoint. And that's also why the derivative of a cusp and the derivative of a corner is undefined or doesn't work, because those left-hand slopes and right-hand slopes would not agree with each other. So if this right here is a polynomial function, those are usually just nice curvy functions, those are always continuous and differentiable for their whole domain, unless there's something extra, we make it a piecewise function and put a hole in it or something. So this is a polynomial function, that means it is continuous and differentiable. So first, I'm going to write that. So f of x is a polynomial. So it is continuous and differentiable. And it's continuous and differentiable from negative infinity to positive infinity. But here, we only really care about out from 0 to 2. So that means that we can apply the mean value theorem. So now we can say that there's some point C so that the derivative at C is equal to the average rate of change from one endpoint to another endpoint. So the first x value that I'm using is 0. So if I plug in 0 to the equation, I get 0 to the third minus 0, and so that's a y coordinate of 0. The other x value for my end is an x value of 2. 2 to the third is 8, so 8 take away 2 is 6. So those are your two endpoints. So we are concluding that the derivative evaluated at C, somewhere there's going to be an instantaneous rate of change or an instantaneous slope that is equal to the average rate of change. So 6 minus 0 divided by 2 minus 0, and that gives me 6 over 2, which is 3. So here we can conclude that there is some value for C where we're going to have a slope of 3. And that verifies what we found in the problem, so we can check that. We just did it. Now they want us to find C. So now we're saying the derivative of the function, so the derivative of the function is 3x squared minus 1. And they are saying somewhere along there there's a C value, not x anymore, we're talking about some C value, where this derivative actually equals 3. So I'm going to go ahead and solve this equation. I can add 1 to the other side, so I get 3 times C squared equals 4. And then I can divide by 3 on each side, so C squared equals 4/3. And for me to solve for C, I just need to square root each side. And anytime I take a square root to solve, I need a plus or minus there. So I've got two answers. C equals positive square root of 4/3. C equals negative square root of 4/3. Now these are x values, right? Because C is a number that is the same as an x value. And if you look at your interval, the interval only goes from 0 to positive 2. So that means that this answer right here is outside of the interval, so we don't care about that answer. It's true, it means somewhere else on the polynomial, that slope of 3 happens again. But the answer that we care about is the square root of 4/3. All right, now we're going to look at Rolle's theorem. So Rolle's theorem says, let f be a function so we're going to write some criteria again. And the first two criteria are the same, so we're going to say that it is continuous on the closed interval from A to B. It is differentiable on the open interval from A to B, so that's exactly the same. And then our last criteria is that the function evaluated at A equals the same number as the function evaluated at B. So these are our endpoints. That means that the y-coordinate of our endpoints are exactly the same. So this means if you want to sketch a picture of this, these are not the only pictures that we could sketch. Let's say here's an A value, here's a B value. If the y-coordinates are the same, it means we got to start in the same spot and end in the same spot, and maybe it goes up and then comes down. Or maybe we could say here's our A and here's our B value, and we're going to have the same, exact same y-coordinates. Maybe it goes up and comes down and goes up and then comes back down. So something can happen, anything can happen in between, but we're saying that the y value of those endpoints is exactly the same. So that's Rolle's theorem. If that happens, then there exists some C. So on AB, such that the instantaneous rate of change at that point is 0. So it means we're going to have some slope in here that is a slope of 0. And you can see how that would, logistically kind of make sense. that if your graph had to like go up and then come back, or go down and then come back, at some point you're going to have a slope of 0 somewhere in between those points. All right, so our example for this problem using Rolle's theorem is going to say, verify the conclusion of Rolle's theorem using f of x equals x squared minus 3x plus 2 on the interval from 1 to 2. So just like before, we have to verify that this function is continuous and differentiable, and this function is a polynomial. And polynomials are continuous from negative infinity to positive infinity, and if that's the case, then it's definitely continuous on these 2 points. Or not on the 2 points, but between them. So it's continuous and differentiable on the interval from 1 to 2. So we check that. To apply Rolle's theorem, we have to say that if I plug in x equals 1 and I plug in x equals 2, the y coordinate I get for each of those is going to be identical. So if I plug in 1, I get 1 squared minus 3 times 1 plus 2. So that gives me the point 1. 1 minus 3 is negative 2. Negative 2 plus 2 is 0. And then if I plug in 2, 2 squared is 4. So this gives me 4 take away 6, which is also negative 2, plus 2 is 0. So here we can conclude that the function evaluated at 1 is equal to the function evaluated at 2. And so we have met the 3 criteria for Rolle's theorem. So since that is the case, we can say, by Rolle's theorem, there exists a C in 1, 2. I wrote that really terribly. Let me fix that. So between the x values of 1 and 2, such that the instantaneous rate of change at C is 0. And yes, you have to write that whole sentence out. Now there's a way to shorthand this sentence, and when you do not have to do it in this class, although if you would like to, you are more than welcome to. So one option is you can write out this whole sentence. Yes, you have to write it. The other option is for you to shorthand it using math notation. So we could say, using math notation, by Rolle's theorem, there exists, so that's the symbol that we use to shortcut there exists a C in 1, 2. So this is saying there's a point C inside the interval 1, 2, such that f prime of C equals 0. So that is how you use math notation to shortcut that sentence, and those are your 2 options. You can either write out the sentence or you can write out the math notation. So by Rolle's theorem, there exists a C inside the interval 1, 2 such that f prime of C equals 0. All right, here is our next example. We want to determine whether the mean value theorem applies to f of x equals 1 over x squared on the interval from 1 to 2. So if you consider this function, we're not talking about a polynomial function anymore. We're talking about a rational function now. And rational functions are not necessarily continuous from negative infinity to positive infinity. In fact, they are often not. So here we have to consider where this function is not continuous. And I can see that at x equals 0, f of x is not continuous. And that's because it has a vertical asymptote right there. So x equals 0, f of x is not continuous. But if we look over here, it's not asking for us to consider an interval where 0 is included. It's asking us about the interval from 1 to 2. And since x equals 0 is not on that interval, it's okay. We're going to say that the mean value theorem actually applies. Because 0 is not on 1, 2. Or if you want to write math notation, you would say that 0 is not on 1, 2. All right. Now we want to do the same thing, but we want to talk about the interval from negative 1 to 2. So does the mean value theorem apply if this is the interval we're talking about? And the answer is going to be no, and that's because 0 really is on that interval. So now we're going to say that this function is not continuous from negative 1 to 2, nor is it differentiable from negative 1 to 2 because there is a discontinuity in the middle of that interval.